స్పీకర్ కూడా ఆన్ చేస్తున్నాను.
ఈరోజు
ఓకేనా?
యూట్యూబ్ ఆన్ చేశాను సార్.
వస్తున్నారమ్మా అందరూ? జాయిన్ అయ్యారా? ఓకే. అలాగే అది 15 నిమిషాల 56 సెకండ్లు స్టార్ట్ అయింది. Good afternoon, participants. I welcome you all to the third day of the web series being organized at the Department of Meteorology and Oceanography, Andhra University. Today we are in the third day of the lecture series, and today we have an eminent speaker, Professor V. Brahmananda Rao Garu from CPTEC, Brazil. It is my proud privilege to introduce Professor Brahmananda Rao Garu to the audience. Professor V.B. Rao did his early education in BSc in Physics from Andhra University, and later he had his Masters in Meteorology and Oceanography from Andhra University, and then a PhD from Andhra University in the year 1968. He started his career as a senior researcher at the National Institute for Space Research, popularly known as INPE, São Paulo, Brazil. And from 1971 to 1998, he has been a senior researcher, and then after that, he retired from active service and became an emeritus professor. He is an active member of the American Meteorological Society and also a life member of the Indian Meteorological Society. In the year 1994, he was awarded the Distinguished Researcher for INPE, and he was awarded the 1998 WMO Prize, and in the year 2000, he was awarded the Adalberto Serra Prize from the Brazilian Meteorological Society. He got a merit certificate in the year 2004 from INPE, Brazil, and then one of his papers in 2009 was published as Nature Research Highlights. And in 2009, since 2009, he has been an emeritus scientist, and for the information of the audience, he is the first Qualis A professor for the entire South American continent. He has supervised more than 25 people for his PhD, and then he had 133 publications, of which more than 100 are in international journals of high reputation. And with these few words, I now welcome Professor V. Brahmananda Rao Garu to give his lecture on the evolution of modern meteorological concepts. Professor Brahmananda Rao Garu.
Thank you, Professor Ramakrishna. Good afternoon to all of you. Before starting my actual lecture about the evolution of modern meteorological concepts, I will recite a sloka from what is called Upanishad. Maybe you all must have seen the emblem of Andhra University. What is written there is Tejasvi Navadhitamastu. This sloka is from, this is a part of sloka from Upanishad, which means Om Shahana Vavat Sahana Bhunaktu Sahaviryam Karavavahaihi Tejasvi Navadhitamastu Mavidvishavahaihi Om Shanti Shanti Shanti. This is, as you know probably, that these Upanishads are almost 1,700 years before Christ. That is about 3,700 years before Christ. Don't think I am talking about the slokas and all, but surely I will in another 5 minutes start talking about the meteorology, of course. What it means for this emblem is Tejasvi Navadhitamastu, means let our education be effective and vigorous. So, for all those students, particularly when you take up any serious study, either for masters or for PhD or for research, you should seriously concentrate on the subject, and the study must be effective and vigorous. That is what is meant by Tejasvi Navadhitamastu. Thank you. And now I will start the evolution of modern meteorological concepts. And probably some of you may be knowing that the first discovery of the Rossby waves was by Professor Rossby in 1939, almost 82 years before the present. And I will, a little later, I will talk about that also. Please, the project చేయండి ఫస్ట్ చూస్తాను టైటిల్ అది కాదు నౌ యూ సీ ఇన్ దిస్ చూస్తుంది కిందకి సరే అయితే యూ ప్లీజ్ సీ హియర్. This is the title of today's talk, Evolution of Modern Meteorological Concepts for Weather and Climate Modeling. As I said, before 1939, meteorology was actually a descriptive science and there is no quantitative analysis. And after 39, when Rossby discovered the so-called Rossby waves, which are responsible for the change of the weather, then it got actually a dynamic base for the prediction of weather. And now, later on, from about 1939 up to 1950, the first prediction. Earlier, there were attempts for the prediction of weather by L.F. Richardson, but that was a failure. He could not successfully predict the weather. The first successful prediction was by Charney and others, Charney, Fidgertoft and von Neumann. In 1950, in a journal called Journal of Meteorology, they published the first successful prediction by means of what is now called numerical weather prediction. And then on, that was actually a barotropic model. What is meant by barotropic is, it is only a one-layer model. And this particular model, the movement of the so-called Rossby wave lower latitude tropics, what actually is important is barotrapic exchanges. What I mean is, in the nature, in the atmosphere, the barotropic exchanges are much less important than barotrapic changes. That is, what is barotropic is the following. If there is a mean current, the energy, the kinetic energy of the mean current changing to kinetic energy of mean current exchanging to the perturbation kinetic energy or for the waves. If it is positive, that's called barotropic instability. Although this type of barotropic instability exists in some regions, but that is very rare. But in nature, in the middle latitudes, it is the barotrapic instability that is dominant, while in the tropics, like the Indian monsoon and other regions, again it is the barotrapic conversions that are more important. Of course, in the case of the tropics, the barotrapic exchange is mostly by the generation of available potential energy by latent heat and subsequent conversion into the kinetic energy. Even in the case of the tropical cyclone, the main energy comes from the liberation of the latent heat of condensation. And now I will show you a simple Now, if you see in this projection, if phi is any meteorological variable, it could be geopotential, it could be temperature, it could be rainfall. And in this case, phi is a function of lambda, the zonal longitude, phi the latitude, z the height, T the time. In this case, this can be divided, divided into phi bar, which is a time mean, as you see here. The arrow No. You see here, phi bar is actually equals to 1 by 2 delta t integral of t minus delta t to t plus delta t phi dt, where 2 delta t is the time interval. It could be 3 months mean, seasonal mean. It could be 6 months mean. It could be 1 year mean. It could be 5 years, 10 years, or even 100 years. Depending on your interest, you can choose 2 delta t. And now, as you see in this, we use the integral in time t minus delta t to t plus delta t, because you cannot start at 0 because it has already started, it's going on. So, at any particular instant, you go minus delta t and then plus delta t, and then 2 delta t is the time interval. Phi bar then is the time mean. And now, and this phi bar again, since it is time mean, in that interval of 2 delta t, phi bar is independent of time. And so, phi bar, a function of longitude, a function of lambda, a function of latitude phi, and function of height z, again it can be divided into phi double bar, which is the zonal mean. That is, if you take a particular latitude circle, 30 degrees north, for example, you take the average of that particular latitude. So, phi bar is the zonal mean. Since it is the zonal mean, it will not vary in the longitudinal direction. So, it is not a function of lambda, but it can vary meridionally and vertically. It can vary meridionally and vertically. And then phi star is the deviation. Phi star is the deviation from the zonal mean. That is a function of longitude, latitude, and the height z. But phi bar, for example, it came from time mean. Phi bar, it came from time mean, so it is independent of time. So phi star also is independent of time. Both the zonal mean and the zonal deviation, in this case, are independent of time. And now, phi double bar is the mean meridional circulation, and as you may be knowing, that this describes actually the so-called tricellular circulation, Hadley, Ferrel cell, and the polar cell. And phi star, it is from the time mean, but varies in the zonal direction. Since it varies in the zonal direction, it is a wave. But since it is actually independent of time, it's stationary wave. And now, so the entire, what you call, meteorology is about this phi prime, the transient, and phi double bar and phi star. These three parameters completely describe the meteorological variation. Phi star is transient variation, so phi star is zonal mean, but independent from time, so they are the so-called stationary waves. Whereas phi double bar is mean meridional circulation, and phi prime describes the time variation. So phi prime is responsible for weather changes. Now I will talk about the first Prof. This is a very, very important paper. I suggest all of you, those who did not read so far, should read this paper. And it is the discovery of the so-called Rossby waves. The so-called Rossby. Okay. So this is a paper by Rossby, C.G. Rossby, Carl Gustav Rossby, and collaborators. And the title is Relation between Variations in the Intensity of Zonal Circulation of the Atmosphere and Displacement of Semi-Permanent Centers of Action. In this case, you see here, in this particular paper, there are several types of innovations. Please remember, this is a first paper which actually describes or the Rossby waves are discovered. In this, there are at least 3 or 4 innovations. What we can see is the genius of Professor Rosby. First, pay attention please, this is important. Instead of using V component and U component, the meridional wind and the zonal wind, then you have to treat two variables. So, Rosby ingeniously used the relative vorticity. As defined here, the relative vorticity, the zeta equals to dV by dx minus du by dy. This is important. Instead of using two variables, V and U, he used only one variable, the vorticity. And of course, actually, these two variables, V and U, corresponding variations would be relative vorticity and divergence. In his case, used only relative vorticity, and now you see here d by dt of zeta, the total derivative, the vorticity equation. If you take the vorticity equation, now maybe many of you are already familiar about this. If you take the more simple barotropic vorticity equation, it is d by dt of f plus zeta equals to 0, or f plus zeta, the absolute vorticity is constant, or the absolute vorticity is conserved. In the case of meteorology, please pay attention. In the case of meteorology, normally meteorologists look for variables which are conserved. Why? Because if you take variable like absolute vorticity, in the case of simple barotropic fluid, d by dt total derivative of f plus zeta equals to 0, f plus zeta, the absolute vorticity is conserved. The conservative properties are useful because you can trace these properties, and thus will be useful for prediction. So if you take a fluid flow, since in this particular case with these approximations, the absolute vorticity is conserved, d by dt total derivative, it gives the Lagrangian derivative. You may be knowing the difference between Lagrangian and Eulerian. In the case of Lagrangian derivative, the total derivative, you follow individual fluid particles. Thus, in this particular case, individual fluid particles, the absolute vorticity is conserved, so you can trace the movement of these particular variations of the particles. Now in this case, if you see for the barotropic vorticity equation, if you write d by dt of f plus zeta equals to 0, then there will be essentially, if you take a zonal average, and then the time average of the zonal wind, you will essentially have only three terms. Yes. Now you see here in this vorticity equation 9, d by dt of zeta equals to u d by dx of zeta plus v d zeta by dy minus v df by dy. df by dy is the so-called beta parameter. It is also often called as the Rosby parameter. And now, if you linearize these equations, if you linearize this particular equation 9, you will have the equation 10, the variation of d by dt of zeta, local derivative d zeta by dt plus u d by dx of x and then you have u prime zeta prime term, and again v prime zeta prime term. The terms in the parenthesis u prime d by dx of zeta prime plus v prime d by d zeta of zeta prime. If you, in the case of small values, these two parameters, these two what you call u prime, v prime terms can be neglected, and finally you will have equation 11, which is actually d by dt of partial derivative of d by dt of zeta prime. You did not use the prime, but actually it is the prime term. Actually d by dt of zeta prime plus u d by dx of zeta prime minus beta v. And now another ingenious, again the assumption that Rossby used. You know very well that the fluid, the thin fluid layer above the surface of the earth, the atmosphere, is spherical. So, actually we have to use the spherical coordinates. But Rossby ingeniously used what's called, pay attention please, what's called beta plane approximation. Beta plane approximation, in this case, is what he used. F equals to, we expand in terms of Taylor series, it will be F equals to F0 plus df by dy into y prime, and the corresponding all the terms. If you take only the first two terms, the linear term, zeta, actually f equals to f0 plus beta y, because df by dy is beta. And now Rossby ingeniously used beta as a constant. And now you see here, now you see in this table 1, what he used in this case, beta as constant. In the analysis, he uses beta as a constant, and to verify how much beta varies, how much actually the error would be if you take beta as constant. In this case, he calculated the value of the beta parameter, and he shows that the beta decreases by about 29% only, from 45 degrees north to 60 degrees north. And like this, he uses beta as a constant. Now, I will further explain the beta plane approximation. Again, this is a very important concept that Rossby used for the first time, the so-called beta plane approximation. Although he uses Cartesian coordinates, he includes the important effect of sphericity through beta parameter, and he takes only f equals to f0 plus beta y, where beta is taken as a constant, as he has shown in the above table. Beta is almost constant within a what you call very near latitudes of equator. In any case, imagine this. Suppose you have a sphere. Think about this. You have a sphere, the earth. Now imagine a cylinder touching on both sides of the equator. I repeat, you imagine a spherical like a ball, and imagine a cylinder in which the ball is put such that the equatorial region touches the cylinder. Now imagine that the radius or the diameter of the cylinder goes on increasing. As the cylinder increases, as the radius of the cylinder increases, it becomes virtually a plane. So, in this particular case, what I was explaining just now is a equatorial beta plane approximation. So, in 1939 itself, almost 82 years ago, Rossby used another ingenious idea, another ingenious innovation, that so-called beta plane approximation. As I said earlier, one innovation is, instead of taking U and V, you use vorticity, and now this is that the beta plane approximation, instead of taking the equator touching the cylinder, if you take very similar at about 45 degrees north or 45 degrees south, it is actually a middle latitude beta plane approximation. What I was explaining is the beta plane approximation for the equatorial regions. And for those of you who are interested further to read about this, there is a paper in the Journal of Atmospheric Sciences, 1964, by Frank B. Lipps, LIPPS. That is the reference. Those who want to read further about the beta plane approximation, they can read this paper, Frank F. B. Lipps, 1964, in the Journal of Atmospheric Science. The title is about the beta plane approximation. This is another very important concept, that in the case of Rossby, he was the first to use the beta plane approximation. Now, you see here, in the case of the equation 18, that C equals U minus beta L square by 4 pi square equals to 0. Now, these waves, again, please pay attention, these are d by dt of f plus zeta equals to 0. These are actually, patent, these are free Rossby waves, because there is no forcing in this. These are the free Rossby waves, and they propagate with a phase velocity of c, and then u is the zonal current. Now in this, if c equals to 0, then it will be a stationary Rossby wave, the so-called, it appears as written here, the stationary Rossby wave, t equals to 0, then u equals to minus beta L square by 4 pi square. Now, pay attention again, these are actually free stationary waves. These are actually free stationary waves, free stationary Rossby waves. There are other kind of stationary waves forced by mountain or heat source and sinks. When these two, what you call the wavelengths, become equal, there is a sort of resonance. Anyway, I will not go much detail about this, and that this particular resonance is now used as what is called the quasi-resonant amplification. When I repeat again, when the wavelength of the free stationary wave becomes equal to the wavelength of the forced stationary wave, then there can be a resonance, and in a recent paper which we submitted to a journal, we use this concept to explain the so-called heat waves over India. Anyway, I will not go further into this, and now I will go to another concept here. Table, that's the table. evolution Oceanography. Yeah. No.
Immediately clockwise.
Now, now you see, I tried to prepare a diagram, and which actually includes several processes, several meteorological and oceanographic process, or some sort of a general circulation, and if I will give several lectures later on many aspects of this particular table. In any case, I divided what you call these process actually of scales of about 1,000 kilometers or about 10 to the power of 6 meters. And now I divided into theory and another observations. In the case of meteorology, both theory and observation and their studies are very, very important. Now, in the case of the stationary, in the case of theory, we can have a linear theory and the non-linear theory. In the case of the linear theory, we get for the stationary, you remember the concept I had written earlier as the phi double bar. The phi double bar actually is the symmetric circulations. Phi bar is zonal average, phi double bar is the zonal and time average. Since it is zonal average, pay attention. If you take a sphere or the earth rotating around its axis of rotation, I repeat, if you take earth rotating around its axis of rotation, now these parameters, phi double bar, as I have written earlier, which is time mean and zonal mean, is actually symmetric. Why symmetric? Because these values do not change in the x direction, so around the axis of rotation, they are constant. So, around the axis of rotation, they are symmetric. What I wrote here, stationary symmetric circulation. What you call constant? Stationary symmetric circulation. And I repeat again, what is phi double bar? Phi one bar is zonal average, phi another bar is time average. Since these values do not change in time, do not change in the zonal direction, they are symmetric around the axis of rotation of the earth. And now, this particular parameter, phi double bar, describes what are called, as I show just now, as I explain a little later, that first Hadley in 1735 and Kuo 1956. For those of you who have already heard the lecture of Professor Hoskins, he gave a theory rather than theory. Actually, it's a observational study, a new perspective of the Hadley circulation. But now I will treat Kuo 1956 problem. Again, another important concept now here is, in the case of the atmosphere, the planet atmosphere, in the case of planet atmosphere, the mean meridional circulation or the phi double bar. while double ball is also called mean meridional circulation. Mean because they are zonal average, mean because they are time average, and meridional because they vary in the meridional direction and in the vertical direction only. If you remember, phi double ball is a function of y and z. So, phi double ball varies only in the zonal, in the what you call meridional direction and vertical direction. So, this phi double ball describes the so-called tricellular circulation. Now, Kuo in 1956, probably the first paper about the so-called tricellular circulations. I will give it is a little bit involved mathematically, but still the basic idea you can easily follow. In the case of the S atmosphere, and also another important aspect is, please pay attention, that these planetary atmospheres like Earth, Mars, Venus, Jupiter, like that, all these planetary atmospheres, the governing equations, that means the equations which govern the fluid flow are the same. And important is Lawrence, Professor Edward and Lawrence gave the name governing equation because these equations govern the fluid flow. So the governing equation of all the fluid flow of planet is the same. The governing are the same, and there is a very, very important chapter in a book by Charney, Jules Gregory Charney, and the title is Planetary Fluid Dynamics. And the equations which govern fluid flow, atmospheric flow, in the case of S atmosphere, are the same for the atmosphere of the Mars, for the atmosphere of the Venus, and like that. Only thing is what changes, the equations are same, or the governing equations are the same. What changes are the parameters like solar constant, rate of rotation, etc. And in fact, I worked also on the baroclinic instability of Mars. Those who are interested can write to me or they can talk to me later. Anyway, I have two papers in Journal of Geophysical Research about the baroclinic instability of the Martian atmosphere. We use the same equation which describes baroclinic instability in the case of Earth's atmosphere. The same equation can be applied for other planets, only this basic constants will change. Now, poor baroclinic. So this is a paper by Professor H.L. Kuo, published in 1956 in a journal called Journal of Meteorology. This journal is not there anymore, and that is divided into two, Journal of Atmospheric Sciences and Journal of Applied Meteorology and Climatology. It's an American Meteorological Society journal, one of the first journals in meteorology. In 1956 December, he published a paper. The title is Force and Free Meridional Circulation in the Atmosphere. He poses a question: in the case of Earth's atmosphere, the mean meridional circulation are forced or free. The mean meridional circulation are forced or free. And what we see in this scale, what is the forcing and what are the equations without forcing? You can answer. No. If you take the equations of motion and then equations of motion and then divide these parameters like u, v, w in terms of u bar plus u prime, v bar plus v prime, w bar plus w prime, where the bars are the mean parameter and the deviations are the perturbations. And then if you take, for example, the term v d by dy of u, and then if you take v equals to v bar plus v prime, u equals to u bar plus u prime, then you have four terms, two bar terms, two perturbation terms. And then the bar terms, where bar is the zonal average, they describe the mean meridian circumference, and the prime describes the perturbation. And finally, you can derive a single equation, what you call a single equation describing a parameter, what he calls a stream function. Here you see this equation 7 you see v equals to 1 by, this is spherical coordinate, 1 by cos phi d psi by dp, and omega equals to minus 1 by a cos phi d psi by d phi. So in this case, v1 u omega 1, where omega is the vertical p velocity dp by dt, and then psi is the stream function which defines the mean meridian of circulation. And if you substitute dv by dy plus d omega by dp, you can see it is 0. In this particular case, if you see these two, dv by dy, d omega by dp, then add, you can easily see that these accepts are the total divergence 0. And this describes, as you very well know, the equation of continuity. The equation of continuity describes the continuity of the mass. I will tell you. You see the equation of continuity 5, the equation of continuity 5. So in this, you have to substitute this V1 and omega 1, d by dy of V1, d by dp of omega, the sum is 0, or it satisfies the equation of continuity or the balance of the mass. And now, finally, if you eliminate, get an equation in terms of a single parameter psi, a little bit mathematics, but don't worry about that. Just a minute, please. And then finally, you get an equation Finally, you get one equation in one variable. Equation 9, the equation 9, one equation in one variable, the variable is psi, and in this case, you can simply think like terms on the left-hand side equals to terms on the right-hand side. The terms on the right-hand side, they have forcing, like H, see? And if you take terms on the left-hand side equals to the forcing F on the right-hand side, and now if you put forcing 0, I repeat, we have a single equation in one variable psi, and this is actually a partial differential equation of second order. And then in this case, this equation has terms on the left-hand side and forcings on the right-hand side. If you put forcings 0, I repeat, if you put forcings 0, then you will have a solution since psi describes the mean meridional circulation. If the forcing is 0, it will give a solution for the free meridional circulation. It will give a solution for the free meridional circulation. If there are forcings also, then it will give a solution for the forced meridional circulation. And now, a little bit mathematics, but simple only. The basic idea is simple. If you put forcing 0, the left-hand side equals to 0, it is a second-order partial differential equation, and the second-order partial differential equation can have solution. It can have three types of the equation. For example, the so-called elliptic or parabolic or hyperbolic. In the case of second order partial differential equation, if it is elliptic, if it is 0, forcing is 0, and if you take a boundary condition also homogeneous, that is boundary also 0, then the elliptic equation has only trivial solution and there will not be solutions. So, in the case of what we call a free meridional circulation, in the case of free meridional circulation, to have a solution, the equation should be either parabolic or hyperbolic. So, that gives a condition that gives a condition 10 here, to have a solution for a free meridional circulation, that gives a condition in terms of, pay attention please, in terms of meridional variation of the zonal mean temperature T0 here. That is d by d phi, or in Cartesian coordinates d by dy of T0 simply, and equals to or greater than, the equals to and greater than gives for the parabolic or the hyperbolic. And so, pay attention, I repeat, in the case of free meridional circulation, in the case of free mean meridional circulation, to have solution, we will have an estimate of the meridional temperature gradient. So I repeat what has been done by Prof so far. He derived a single equation in terms of stream function. which describes the mean meridional circulation. This has a forcing on the right hand side in terms of the basic eddies like V prime, U prime, V prime, T prime, terms of that type. And then if you put this 0, then the second order partial differential equation can have solution only if it is parabolic or hyperbolic. That is given in terms of the equation 10 here. The greater is, I think, parabolic, equal to 0 is hyperbolic. In any case, that is given in terms of the gradient of temperature in the meridional direction. In the case of the Cartesian coordinate, what is given is d by dy of T0 or d by dy of the zonal average of temperature. If it is equal to 0 is the minimum condition, greater than 0 is another condition for existence of free mean meridional circulation. So, with this you can calculate the mean meridional circulation, which can have a free meridional circulation in terms of the meridional gradient of temperature. You can calculate this. Let us say it is A, capital A. Pay attention now, please. So, to have free mean meridional circulation, the condition is given in terms of the meridional variation of the zonal average temperature. Let us call it A. And now, for those of you who are aware of the Berkeley instability, for the Berkeley instability to occur in the case of H atmosphere, let us say that is also given in terms of the shear, vertical shear, or in terms of thermal wind if you use, is equal to meridional gradient of temperature. Because for the thermal wind, meridional temperature is proportional to the vertical variation of the zonal wind. So, now I repeat again. For the existence of free mean meridional circulation, let us say the value is A. You can calculate that value because in this equation 10, we know all the terms. Then we can calculate the gradient of temperature for the existence of free mean meridional circulations, and we also can calculate the gradient for the Berkeley instability, the existence of Berkeley instability. Let us call that is B. So A, the value A is for the existence of free mean meridional circulation, and B for the existence of Berkeley instability. Now, the most important aspect of Earth's atmosphere is B, the mean meridional temperature gradient B is much smaller than A. Or in other words, to have a free mean meridional circulation A, the value is much higher than B, which is necessary for the occurrence of Berkeley instability. So, pay attention. So, in the nature, if you take an atmosphere, sun hitting the atmosphere, the earth gets the temperature, higher temperature in the equatorial regions, and then the lower temperature in the polar regions, and the temperature gradient goes on building up. Let us say 1, 2, 3 like that. So, B the smaller value, smaller than A occurs first. So, the waves become unstable first, and then once the waves become unstable volcanically, they start transporting heat from the equator to the pole. So that value necessary for the pre-meridional mean meridional never occurs in the case of atmosphere. I repeat again, Kuo derived a condition for the free mean meridional circulation. That is given in terms of the gradient temperature in the meridional direction. Let us call A. And we also know for the Bernoulli instability to occur, it is again the mean temperature gradient in the meridional direction B, let us say. But the value B for the existence, for the first occurrence of Bernoulli instability is much smaller than A. So the waves become first unstable. The waves become first unstable and start transporting heat meridionally, and that value necessary for A never reaches the atmosphere. So this is the crux of the main point in the case of the atmosphere, Earth's atmosphere plane. There are other atmospheres. For example, in the case of Venus, it is the meridional circulation that are dominant. So, in the case of Earth, for example, the waves, because barometric instability generates barometric Rossby waves. So, in the case of Earth's atmosphere, the waves are dominant and the mean meridional circulation is very weak. So, pay attention. In the case of Earth's atmosphere, if you think of two regimes, Rossby regime and the Hadley regime, for the Earth's atmosphere, it is the Rossby regime that is the dominant. Whereas in the case of other planets, for example, for Venus, it is the Hadley regime that is dominant, but for Mars again, it is the Rossby regime. But I want to use the next evolution of modern meteorology concept in Langalan. The only problem. ఇంకా నెక్స్ట్ ముందు ఇంకొంచెం ముందు వెనక్కి దానికి వెళ్ళండి దీంట్లో వెనక్కి ఇది టేబుల్ ఉంది ఈక్వేషన్స్ అది ఇది చూపించాం తిరగండి Now I show you energetics calculated from observations. You can see here energetics calculated from observations by Wood and Picciotto. Since these are calculated from observations, they are the fact, the realistic values. Now in this case, you see, you see P bar means generation of, P bar means available potential energy, mean available potential energy, P prime is the eddy available potential energy, and K prime is the eddy kinetic energy, and K bar is the mean kinetic energy. And now P bar to P prime, the conversion from P bar to P prime, this is given, for those of you who are already known about this, P bar to P prime actually is given by, in terms of an integral of du by dB into V prime T prime bar. Actually, the conversion of zonal mean available potential energy to perturbation kinetic energy is given in terms of transport of meridional transport of sensible heat, and then P prime to K prime, that is the conversion of perturbation available energy to perturbation kinetic energy is given in terms of P prime, K prime is omega prime, alpha prime. That is the vertical transport of sensible heat, omega prime, alpha prime. And K prime to K bar is given in terms of integral of du by dy is V prime U prime bar, where V prime U prime bar is the transport of momentum. And now what is important is the following. You see the numbers here. What you call P bar P prime is 1.5, the same scale. Same scale, 10 to the power of 5 joules per meter square. P bar to P prime is 1.5, P prime to K prime is 2.2, and this P bar to P prime to K prime is the typical energy cycle of a baroclinic wave. Whereas K prime to K bar is barotropically stable wave, because K prime decreases and K prime increases. Or P bar to P prime to K prime is typically baroclinically unstable, what you call energy cycle. Now you see P bar to P prime 1.5, P prime to K prime is 2.2, K prime to K bar is 0.3, and K bar to P bar is again 0.2. So pay attention. 0.2, 0.3 are one order of magnitude smaller than 1.5 and 2.2. Or pay attention. In the case of Earth's atmosphere, as calculated with observation, that is reality, actually happening. These circulate, these exchanges, P bar to P prime to K prime, are baroclinic waves are dominant, and K bar to P bar, mean meridional circulation, is very small. Or this again proves observationally what is arrived at theoretically by Kuo, that, pay attention please, that Earth's regime is Rossby regime, not Hadley regime. So please, and then for those of you who are interested, I want to continue these lectures further in future. Professor Ramakrishna will arrange and he will inform to you all, for those of you who are interested. I want to continue to give the whole structure, the entire structure of the, what you call the table I have prepared. Thank you.
కూర్చోండి సార్ క్వశ్చన్స్ ఉన్నాయి
చెప్పండి. విన్నారా ఎవరన్నా?
శ్రావణి అడుగుతుంది, in the energetics, which term plays the major role in monsoon circulation during, especially during active and break cycles?
Yeah, in the case of the monsoon, normal monsoon, it is the generation of the available potential energy. In this table here, it is the R prime that is given as 0.7. In the case of monsoon, the liberation of the latent heat of condensation is the dominant term, and Professor Ramakrishna has published a paper in Annals Geophysics, and there it is clearly shown that the generation term is very important. That is the term, actually it is the correlation between liberation of latent heat of condensation and temperature. That is Q prime, T prime. This is the major term, and P bar to P prime is very, very small, because there is no transport of sensible heat in the case of the monsoon circulation. The generation by latent condensation that is important. In the case of break and the active monsoon cycles, in the case of break monsoon, since there is no actually liberation of latent condensation for most of the country, not most of the country, only in those regions. In my knowledge, there is nobody who has calculated this. That will be an interesting study, Dr. Sramani. That will be very interesting to calculate analytics for the break and active cycles. What causes the changes, the energy cycle, the complete energy cycle of several breaks, and then compared that with the active monsoon. That will be a very important study. To my knowledge, nobody has calculated that.
Another question, sir. It is from Srinivas Gangiredra, who is a postdoc in France. What is the important feedback process that involves in tropical Pacific precipitation? Is it convergence feedback or thermodynamic feedback, and how it is controlled?
Please repeat.
What is the important feedback process that is involved in the tropical Pacific precipitation? Is it convergence or thermodynamic feedback?
Convergence of water. Please.
తెలియదు మరి అంటే ఈ ఇంపార్టెంట్ ఫీడ్బ్యాక్ ప్రాసెస్ అన్నాడు. ది క్వశ్చన్ ఈజ్ వాట్ ఈస్ ది ఇంపార్టెంట్ ఫీడ్బ్యాక్ ప్రాసెస్ దట్ ఈస్ ఇన్వాల్వ్డ్ ఇన్ ట్రాపికల్ పసిఫిక్ ప్రెసిపిటేషన్. Dr. Srinivas, you may pose the question in person to Professor V.B. Rao garu. I will send you his mail. You can contact him in person.
Because the question is not clear to me, please.
Yeah.
Because you are talking about the energetics of the ocean or the energetics of the atmosphere.
Moisture convergence.
Moisture convergence. Normally, by and large, in the tropics, is the liberation of latent condensation that is important, not the what you call the sensible heat from the ocean. Maybe in the case of even tropical cyclones also it is like that. What you call the feedback of what I could not clearly understand. You can send me an email, please, later. Okay, thank you.
Thank you, sir.
Srinivas
శ్రీనివాస్ అండి ఇక్కడ చేశారు పిహెచ్ మీరు ఇలా వచ్చింది ఓట్ ఆఫ్ థ్యాంక్స్ చెప్తారు.
Good evening to all. I thank all the researchers and students attended for the lecture entitled Evolution of Modern Meteorological Concepts, delivered by Professor V.B. Rao garu, INPE, CPTEC, Brazil. We know that at the age of 80 years, Professor V.B. Rao garu has been publishing high-quality research papers in highly reputed journals like JAS, JCR, Nature, etc., by motivating the present generation. No doubt to say that Professor Rao garu inspired so many young scientists. Sir, you are our proud alumnus. You were awarded with master's degree in Meteorology and Oceanography and a doctoral degree from our Department of Meteorology and Oceanography, Andhra University. You are trained under supervision of a great legend and intellectual as well as great human being in the scientific community, Professor Rakam Ramanath Garu. Your talk has given immense pleasure and new energy to many youngsters to move further into research field. Thank you very much, sir, for delivering very informative lecture. Thank you once again, sir.
Thank you, thank you.
Yes, yes, sir.